Whiplash is a serious public health issue around the world. Experts estimate that nearly 1 million people in the U.S. are injured each year in rear-end automobile collisions, with an annual cost of about $30 billion. Whiplash injuries are a modern phenomena. The term whiplash was first used in 1928, and whiplash injuries started to become more common after World War II with the rise in popularity of the automobile. Whiplash has been controversial since the 1950s, and remains so 50 years later. The greatest debate regarding whiplash today is the area of low-speed collisions, especially injuries arising from accidents with little or no visible vehicle damage. Most people are not aware that there have been literally hundreds of studies written on the problem of whiplash, and that since 1995, a number of respected scientists from around the world have made some exciting new discoveries that have uncovered how the human body can be injured in low-speed rear-end collisions. The goal of this video is to acquaint you with these discoveries, show you how low-speed rear-end collisions result in abnormal motion of the human spine, and describe some of the factors that can increase the risk of occupant injury in these collisions. This information can help us understand and treat whiplash pain, and can direct us to new ways to reduce the number of these injuries in the future. To understand the complexity of whiplash injuries, we first need to look at the basic physics of rear-end collisions. These simple concepts of physics explain how the vehicles and the occupants move during a crash. There are three concepts we need to understand: momentum, acceleration, and inertia. Momentum is simply the energy of a moving object and is mathematically described as being equal to the mass or weight of an object multiplied times its velocity or speed. From this equation we can see that the heavier an object is, or the faster it is moving, the more momentum it will have. For instance, a 2,000-pound car traveling 5 miles per hour will have only half the momentum of the same car traveling 10 miles per hour. Also, a car that weighs 2,000 pounds and traveling 10 miles per hour will have half the momentum of a 4,000-pound car traveling at 10 miles per hour. Momentum also has another important property. According to laws of physics, momentum in a collision is always conserved. That is, when two objects collide, the momentum that existed before the collision must be present after the collision. This is written as follows. As we see here, the momentum of vehicle 1 and vehicle 2 before the collision must equal the momentum of vehicle 1 and vehicle 2 after the collision. This is known as the law of conservation of momentum. Let us see how this relates to automobile crashes. First, we'll start with a car stopped at a red light. This is known as the target vehicle. It has a mass of 1,000 kilograms, but it has a velocity of 0 and therefore has a momentum of 0 as well. Now, the car behind this, known as the bullet vehicle, also has a mass of 1,000 kilograms, but is moving at 5 meters per second, or about 11 miles per hour. Therefore, before the collision, we have a momentum of 0 for the target vehicle, plus a momentum of 5,000 for the bullet vehicle, for a total momentum before the collision of 5,000. According to the law of conservation of momentum, the momentum after the collision must also be 5,000. But once the bullet vehicle strikes the target vehicle, the speeds of the two cars are different. After the collision, we find that the bullet vehicle has slowed from 5 meters per second to just 1 meter per second. Therefore, the momentum of the bullet vehicle is 1 times 1,000, or 1,000. Since the law of conservation of momentum requires that the momentum must be 5,000 after the collision, that means that the target vehicle must have a momentum of 4,000, and thus a velocity of 4 meters per second. That means that the target vehicle accelerated from 0 meters per second to 4 meters per second. Let's look at a different example, where the bullet vehicle has the same velocity as before, 5 meters per second, but weighs twice the target vehicle, or 2,000 kilograms. Instead of a momentum of 5,000, the bullet vehicle now has a momentum of 10,000. The target vehicle is again stopped and has a momentum of 0. So before the collision, we have a total momentum of 10,000. The bullet vehicle in this example slows down to 1 meter per second after the collision, resulting in a final bullet momentum of 2,000. To equal the momentum of 10,000 prior to the collision, the target vehicle must have a final momentum of 10,000 minus 2,000, or 8,000. Since the mass of the target vehicle is 1,000 pounds, the final velocity must be 8 meters per second. So, because the mass of the bullet vehicle was twice the target vehicle, even though the speed of the collision was the same as the first example, the velocity of the target vehicle has doubled from 4 meters per second to 8 meters per second. In other words, although the speed of the crash was the same, the collision was twice as severe because of the increased weight of the bullet vehicle. These two examples are simpler than what really happens during a collision, as we'll see later. But it does graphically illustrate that when we are looking at rear-end collisions, we need to not only examine the speed of the collision, but we also need to take into consideration the weight of the two vehicles involved in the crash. The second concept of physics is acceleration. It is described mathematically as delta v divided by delta t. Delta is simply the Greek symbol that means change in. So acceleration is the change in velocity of the object divided by the amount of time in which the acceleration takes place. In our earlier example describing momentum, we saw that in one instance the target vehicle accelerated from 0 meters per second to 4 meters per second. In practically every study on low-speed rear-end collisions, the amount of time that this acceleration takes place in is about 100 milliseconds, or 0.1 seconds. If we put these numbers into the equation for acceleration, we get a result of 40 meters per second squared. In the second example describing momentum, we saw that the target vehicle accelerated to 8 meters per second in the same amount of time. Thus, the acceleration in the second example is 80 meters per second squared. To simplify matters, engineers often use the term g-force as shorthand to describe acceleration. A g refers to the amount of acceleration that Earth's gravity exerts on objects. For instance, normal Earth gravity is 1g, and the complete absence of gravity is 0g, or zero gravity. Mathematically, 1g is equal to 9.8 meters per second squared. To calculate g-forces, we can simply divide the acceleration of the car, which was 40 meters per second squared in the first example, by 9.8, and we get a result of a little over 4 g's of acceleration. The final concept of physics that we need to understand when dealing with low-speed collisions is the idea of inertia. Newton's second law states that every body continues in its state of rest or uniform motion in a straight line insofar as it may be compelled to change that state by the action of some outside force. In plain English, this simply means that a stationary object will never move unless something else acts upon it to make it move. Likewise, an object that is moving will continue to move until something makes it stop moving. We can look at our earlier car crash model and see inertia at work. The target vehicle is stopped at a red light and will stay stopped until something makes it move. In this example, the bullet vehicle. Likewise, the bullet vehicle will keep moving forward until something makes it slow down. In this case, the car in front of it. And most importantly, inertia plays a critical role in how the human body moves during a crash, and is the primary reason why people get hurt in low-speed impacts. Let's now review the basics of a rear-end collision. The target vehicle is stopped at a red light. The bullet vehicle has both mass and velocity, and therefore it has momentum. The bullet vehicle strikes the target, applying an external force to the target vehicle. The target vehicle is accelerated forward rapidly. Now that we understand what happens to the cars during a rear-end collision, we can now examine the motion of the occupant inside the vehicle.